Anybody heard of the let's make a deal problem or the Monty Hall problem? Yeah, there was a game show called Let's Make a Deal. And one of the things that happens in the game is that there are 3 doors, one of which hides a brand new Corvette, and one of them hides a goat, and the other one has a year's supply of hay for the goat, or something like that. So there's a prize that you want, and then a couple of things that are jokes, okay? And what happens is you're offered a chance to pick a door, and after you've picked the door, the host, Monty Hall, shows you that the prize you want is not behind one of the doors you didn't pick. Okay, so you pick door A, and the host shows you that door B has the year's supply of hay. And the question now is it better strategy to stick with your original guess or to switch your guess to door C? He offers you now a chance to switch. He shows you that the grand prize is not behind a door you didn't pick and offers you a chance to switch. Should you switch? No, yes, yes, no, yes, no, maybe. Who cares? Who wants a Corvette anyway? Yeah. Okay, so what makes this more entertaining is that this question was posed to Marilyn Vos Savant, the world's smartest human. The Ask Marilyn column, I don't know, is she still an active column? Yeah, okay. So, and she said that you should switch. And a handful of university professors wrote back to her saying, you're wrong, here's the math, you shouldn't switch. Conditional probability that the prize is behind door C, given that it isn't behind door B, is 50%. And so you're wrong, Marilyn. All right, so the question is, who's smarter, Marilyn or the professors? So here's a model of the game. So Monty offers me a chance to pick a door. I pick door A. Monty shows me that the prize is not behind door B. Now I have a chance to switch. Should I stick with my original guess or pick door C? I'm going to stick with my original guess. Oops, it was actually behind door C. I would have lost. Okay, so again, I pick door A. Monty shows me it isn't behind door C. I'm going to pick door B. Oh, I won. Okay, proof. No. We're actually going to look at doing this over and over again and figure out what the probabilities are that you would win a certain number of times with a particular strategy in repeated play, and see if we can use that to figure out empirically what the right answer is. But first, we're going to work on it theoretically. Yes?
Would you say, or would you pick a different number?
We'll get there in excruciating detail. All right, so I picked door A. He showed me it isn't behind door B. I stick with my original guess. I lost. Okay, these are, by the way, this really is being done as randomly as I can do it with a computer, right? The computer is hiding the prize behind a door at random, and after I click, it is showing me a door that the prize is not behind, and it's not then moving the prize, right? It's sort of the prize is staying where it was, and I get to pick another door. So I'm going to stick with A again. Oh, that time I won by sticking with door A. Okay? All right, so what's the better strategy? All right, so what are the rules of the game? So we're going to assume the prize is hidden at random. There's a chance of a third of it being behind each of the 3 doors. I'm going to pick a door at random. It really doesn't, if the prize is hidden at random, it sort of doesn't matter how I pick, but the point is that I don't have any information about what door hides the prize. So I'm not able to sort of exploit something to do a better job at that stage. Then an important rule is that the host is never going to open a door and say, there's the Corvette, you didn't get it, right? Not until after the next round, right? The door he opens is always going to be a door that doesn't have the prize behind it. Okay? So far, so good? All right. So here is the naive argument. So don't switch, because after the host shows you what's behind one door, there's 2 doors left. The prize is equally likely to be behind either one. There's no advantage to switching. Doesn't matter whether you switch or not. Okay? Now, it was true when the game started that the prize was equally likely to be behind any of the 3 doors. The question is, when you rule out a door, is it now equally likely to be behind the two remaining doors or not? Okay, this argument says it is. All right. So here's a more sophisticated argument, which is kind of what the professors were saying. So let's call the three doors A, B, and C. Capital A is the event that the prize is actually behind door little a. Capital B is the event that it's actually behind door little b, and so on. So the event B complement is the event that the prize isn't actually behind door B. Okay? That is, it's actually behind either door A or door C. Now, let's suppose I pick door A. The host then shows me that it isn't behind door B. What's now the probability, the conditional probability that it's behind door A versus behind door C? So the calculation would be, what's the probability that it's behind door C given that it isn't behind door B? Well, that's the chance that it's behind door C and not behind door B, divided by the chance that it's not behind door B. This is just the definition, right? But in order for it to be behind door C, it can't be behind door B. So the intersection of C and B complement is just C. C is a subset of B complement. That make sense? It's behind door C. It wasn't behind door B. You already know that. All right, so this is just P of C divided by P of B complement. P of C, that's the chance the prize was originally behind door C. That's a third. The chance that it wasn't originally behind door B is 2/3. Right? So that conditional probability is a half. Okay? And similarly, if you find the chance that it's behind door A, given that it isn't behind door C, you get exactly the same number. It's a half. So according to this argument, there's no advantage to switching. That's what the professors claimed.